Hi, my name is Ingo Müller, and today I'm going to tell you why strong consistency is not hard to get. In this experiments and evaluation paper, we ran two-phase locking and two-phase commit on thousands of cores and observed competitive performance and scalability. Our work is motivated by recent advances in transaction processing, which have shown renewed interest in the field, but also highlighted some challenges. In particular, many approaches proposed in the recent past give up some sort of functionality in order to get good performance and scalability. For example, some systems give up strict serializability and only implement some weaker isolation levels such as snapshot isolation. Other systems make restrictions on long-running transactions, for example by not supporting them at all or by not allowing them to modify the database state. A promising class of systems is based on deterministic data access, but that initially only supported partitioned workloads. More modern versions of this class still overcome that limitation, but still require the read and write set of transactions to be known ahead of time, or at least to be discovered through repeated execution, and that only works with stored procedures and not with interactive transactions. Overall, all of these systems make the assumption that two-phase locking and two-phase commit are too slow to be practical and that some other mechanism is required for good performance and scalability, even if that makes sacrifices in terms of functionality. In this work, we want to challenge that assumption and ask ourselves whether it is still true on modern high-performance networks. To that aim, we use low-latency communication primitives to implement distributed concurrency control mechanisms on modern networks. More concretely, we built a system prototype for distributed transaction processing following a textbook architecture. In that architecture, we have a transaction processing layer consisting of transaction processing agents, which is distributed across the entire cluster. Data is managed by a data layer, which is sharded across the cluster as well, and which collocates log tables alongside with the data in order to protect it from concurrent access. The transaction processing agents use the log table to implement two-phase locking, and they run two-phase commit at the end of each transaction through direct communication. As I mentioned, that architecture isn't new in itself. What is new is how we implemented the low-latency communication layer. And we implemented it using a library called FOMPI, Fast One-Sided MPI, which gives us a 1 microsecond latency across the entire cluster of several thousand cores. In summary, we implemented a simple, traditional, yet powerful design of a log table, and that gives us essentially anything that transactions may ask for. Concurrent readers, hierarchical locking, arbitrary transactions, and so on. It also achieves strict serializability and hence doesn't make any compromises in terms of isolation level. We conducted the experiments on a high-end supercomputer with a state-of-the-art network. We used the Cray XC40 supercomputer in the Swiss National Supercomputing Center using up to 4096 cores. That supercomputer has an Aries routing and communications ASIC for its network, which uses a Dragonfly topology. We implemented several variants of two-phase locking and two-phase commit with different network detection and avoidance mechanisms. As a reference, we also implemented timestamp ordering. For the workload, we use a log trace that we produced using MySQL running TPC-C in different isolation levels. We start with a weak scaling experiment without contention in order to show that our implementation can scale to thousands of cores. In this plot, on the x-axis, we increase the number of transaction processing agents alongside with the number of warehouses managed by our system. On the y-axis, we show the throughput in terms of successfully terminated transactions. What you can see by the straight lines is that all combinations of isolation levels and concurrency control mechanisms essentially achieve linear scalability until the full size of the cluster. What you can also see by looking at the dotted lines, which correspond to strict serializability, is that isolation levels has a certain overhead when compared to the weaker isolation levels. However, that overhead is limited. The difference is never more than factor 2. Finally, if you compare the different markers, you see that in this experiment, the deadlock avoidance and detection mechanisms don't have a huge impact. If we compare these numbers with numbers published by other authors in the past, we see that the numbers that our implementation achieves are actually really competitive. Note that the other systems use a cluster that is roughly factor 2 smaller than ours. The most competitive numbers in this comparison is therefore that of NumDB. However, that system does not implement strict serializability, whereas our two implementations do. We conclude from this experiment that two-phase locking and two-phase commit are actually very competitive, which may come to a surprise. In the next experiment, we add contention to the picture in order to show that scaling to thousands of cores requires not only a scalable system, but also a scalable workload. On the left, we use at most 64 warehouses, and what happens here is that as soon as we have more transaction processing agents than warehouses, the contention limits the performance that we can get. Some combinations, in particular timestamp ordering, are still able to increase the performance using more transaction processing agents, but not linearly. And all combinations eventually plateau in terms of performance or even decrease. If you compare the dotted lines here on the bottom, representing different variants of two-phase locking and two-phase commit, with the dotted lines here on the top, then which correspond to timestamp ordering, you see that timestamp ordering does have a significant performance advantage. If we look at lighter contention, we see that as long as the number of transaction processing agents is smaller than the number of warehouses, 1024, we still have linear scalability. However, past that point, we get a similar effect as before, namely performance plateaus. Overall, we can conclude that workloads with contention, unsurprisingly, have only limited scaling. Finally, we look at what happens with a higher network latency than our supercomputer, and while this does reduce the overall throughput, it also shows that modern networks, both on-premise and in the cloud, are actually competitive. What we did in this experiment is that we added an artificial network delay between 1 microsecond and 1 millisecond to every network operation that we do. Let's first look at an additional delay of 1 microsecond, which roughly corresponds to high-performance commodity hardware such as Infiniband EDR. And if you compare these numbers, if you look at these numbers, they are actually almost the same as what we achieved on the supercomputer. Even if we look now at the numbers of 16 microseconds, which places us at what Amazon promises to provide with their elastic fabric adapter between virtual machines in their cloud, we still have a performance drop of, in quotes, only 30%, which one could argue is still in the same ballpark. Overall, we think that our results are not only valid on supercomputer, but are transferable to commodity hardware and the cloud. To summarize, in this work, we studied the question how modern networking hardware affects concurrency control. We implemented textbook designs of two-phase locking and two-phase commit, as well as timestamp ordering on state-of-the-art networks, and showed that this combination can scale to thousands of cores and achieve competitive performance. What this means is that the concurrency control mechanisms themselves are not the bottleneck on modern hardware, and that many of the compromises done in prior work regarding isolation level or transaction types are often not necessary. While we run our experiments on a supercomputer, we believe that our results also hold on commodity hardware and in the cloud. Finally, we believe that the performance of this textbook design can further be improved, for example, using smart networks interfaces, on which we will be able to offload some of the logic of the concurrency control mechanisms. That concludes my talk, and I'd be happy to answer your questions.